What's up, everybody? Welcome to another video. Hope you're ready to flex those brain muscles. In this video, I'm going to talk about a perspective we could take toward the process of equation solving. And this is a very deductive perspective where we're almost viewing this process as proof. So I hope y'all enjoy and get something out of it. I think this is really interesting. But first, let's talk about the way we traditionally discuss and even teach equation solving. So typically what we do is we start with an equation, we want to solve it, so we treat it as a thing, right? This equation is an object and we're going to manipulate that thing by doing the same thing to both sides. And we often use a metaphor where it's like dealing with a scale or a balance beam, right? If I add to this side, I have to do the same thing to that side to balance it out. And as long as I do that, then I end up with equivalent equations until eventually I isolate this x, and that is our solution. So going from here to here, what we'll do is we'll add 5 to both sides, and we'll often write out what we do to both sides below or next to it, right, to keep track of it. We add 5 to both sides. From here to here, we divide both sides by 3, or we could think of it as multiplying both sides by 1/3, same thing, right? So as long as we do the same thing to both sides, eventually we isolate that x, and that's going to be our solution, x equals 2. So I'm not saying there's anything wrong with this perspective or teaching or solving equations in this way. I'm just going to introduce a different way of discussing this process and viewing this process. And again, it's as a process of deduction. So instead of starting with a thing that we're going to do stuff to, we're going to start with a statement. And what our statement actually is technically it's an assumption. We're going to suppose that x is a real number such that 3 times that real number minus 5 equals 1, right? This is an assumption, and I want to make clear that we actually, a lot of times, we approach solving equations. So like, for example, certain radical equations. We approach solving them without even being certain whether there even is a solution, right? So there is sort of always this implicit assumption that, well, let's assume there is a solution and see what happens, right? And when there isn't, we end up with some kind of contradiction like 1 equals 2. So we can even take a deductive perspective toward that. But let's continue. I don't want to get off too far here. So these will sort of have justifications here because, again, this is a statement. We're viewing this as a statement or an assumption. Suppose that this is true. Then where does that lead us? How does that lead us to here? Well, this statement leads us to this statement using this justification, which is that A equals B if and only if A plus C equals B plus C. And this is true for any real numbers, A, B, and C, right? So this if and only if means that this goes both directions. So if we're given that A equals B, then we can conclude that A plus C equals B plus C. And if we know that A plus C equals B plus C, then we can conclude that A equals B. And in this case, we are going this direction. And if you can't quite see it, let me just rewrite it. We have 3x, and I'm going to rewrite this as plus negative 5, because that's the same thing as minus 5, right? And here we have 6 plus negative 5. Which is equal to 1. 6 plus negative 5 is 1. So really all I've done from this step to this step is some rewriting. I haven't actually changed anything. I rewrote 1 as 6 plus negative 5, and I rewrote minus 5 as plus negative 5. But now we can clearly see how we're going from A plus C equals B plus C to A equals B, right? In this case, our C is negative 5. We have 3x plus negative 5 equals 6 plus negative 5. Therefore, 3x must equal 6. So again, we're treating this as a statement. This statement, then this must be true. Then, because of this justification here, this must be true. Now, how do we get from here to here? We're going to use another justification, which is that A equals B if and only if A times C equals B times C. But here we do need a condition, very important condition that we need to add, which is whenever C is not to 0, because think about when C is 0, what could happen? Well, we could have 1 times 0 equals 2 times 0. That's a true statement because we get 0 equals 0, right? But 1 does not equal 2. So going from A times C equals B times C to A equals B, that only works in general if C is not 0. When C is 0, we can't make that claim in general. That's going to come up a little later, so keep that in mind. But how are we using this justification to go from here to here? Well, let's do another little bit of rewriting. 3 times x, I'm not rewriting that at all. That's just 3 times x, but 6 we can rewrite as 3 times 2. So we have 3 times x equals 3 times 2. Therefore, x must equal 2. So in this case, our C is 3. So technically, we could switch both of these. It would line up better with this, right? Our A is x. Our B is 2. So since 3 times this number x equals 3 times 2, x must equal 2. So again, we're writing an assumption and we're making logical deductions until we reach a logical conclusion. We're viewing this almost as proof, right? What statement did we just prove? Well, we just proved that if x is a solution to this equation, then x equals 2. That's the statement that we've just proved. So why is this important? Well, first of all, I just think it's interesting. I think attempting to take different perspectives toward different areas of math sort of expands your mind a little bit, allows you to think in different ways. That just helps you as a math person. Additionally, I think this could potentially provide students with an opportunity to engage in deductive reasoning. They don't get a lot of opportunities to do this. They don't get a lot of opportunities to do proof, especially at the K-12 level. And since this is really just a 2-step linear equation, it's something that, even a middle schooler in pre-algebra or algebra 1 in high school could engage with and could use these justifications and think deductively. Lastly, I think it helps certain things make a little bit of sense. So I want to point one thing out, which is that really all we've proven from here is that if x is a solution of this equation, then x equals 2, right? That doesn't necessarily prove that 2 is a solution and is the only solution, right? In other words, that the solution set for this equation is the set containing 2. How we would claim that and really prove that is proving the converse as well, right? Because then what we would have is 3x minus 5 equals 1 if and only if x equals 2, right? But we still don't really do that. We don't have to check our answer in practice whenever we're solving linear equations. And the reason why is because technically the converse here is sort of already informally proven, okay? Because what we can do is, let's say, well, to prove the converse, we do the same thing. Suppose x is a real number such that x equals 2. Then we can literally just reverse all these steps, work backwards until we get to this conclusion. In other words, the proof of the converse of this statement is this proof written backwards, right? Rewritten backwards. And that is because that all of these justifications are if and only if statements. That's the reason why we're able to do that, is all of these deductions that we've made, right? All of these conclusions can all be reversed because of this if and only if. So we run into trouble whenever we use justifications that are not if and only if. And this helps maybe potentially, for me at least it does, may help make sense a little bit more of extraneous solutions, right? What are those justifications that we use that lead to those extraneous solutions, and how can we think about that deductively, okay? So hopefully you find this at least a little bit interesting. Let's look at one more example where we get an extraneous solution and write out all the justifications and see if we can point out why exactly it's the case that we get the extraneous solution and when those actually occur. All right, so let's finish off the video by looking at this rational equation. How we would typically approach solving this equation is multiplying both sides of it by the least common denominator to get rid of all the fractions. In this case, that happens to be 12x, so we multiply both sides by 12x. We clear out all those fractions, then we can distribute, cancel, factor, and solve using the zero product property. We end up with two potential solutions, and what we typically always teach our students is when you're solving these rational equations, you have to go and check your solutions. But we often, I feel like, don't do the best job of explaining why sometimes these extraneous solutions occur. Like in this case, this x equals 0 is not a solution to this original equation, although -4 is. Why does that occur? And I think this can be explained using this deductive perspective. So I've written this out as if it were a proof. We are proving if x is a solution to this equation, then x equals 0 or x equals -4. And here are the ways we are justifying each step. To go from here to here, we're using the fact that if A equals B, then A times C equals B times C. And this is regardless of whether C is 0 or not. This works for all real numbers, right? So we can go from here to here, no problem. Then we can use the distributive property. We can use the same property we used in the last example, this additive equality, or you could think of it as cancellation, right? Distributive property again, and fun fact, factoring is just an application of the distributive property. Then the zero product property to conclude that x equals 0 or x equals -4. So this is a pretty nice proof that if x is a solution to this equation, then x equals 0 or x equals -4. But again, all we've proven so far is this forward direction. So what this really tells us is that we have 4 possibilities for solution sets, right? Based on this being true. We have the empty set, right? There could still be no solution, and this would be true vacuously. We could have the set containing 0, the set containing -4, or the set containing both 0 and -4, right? 4 possibilities for solution sets. So really what proving this conditional statement does is it gives us a list of potential, of possible solutions. If we have the proof of the converse statement in front of us, then we can conclude that not only are these potential solutions, they are actual solutions, and they're the only solutions, like we did in the last example. That's the problem. That's the difference between this example and the last example, is we don't have the proof of the converse written in reverse order, right? We can't assume x equals 0 or x equals -4 and conclude that this must be true as well, and it's really because of this if-then statement. This justification does not go both ways. It is not an if and only if. That's only true under the condition that C is non-zero. But x being 0 is one of our assumptions, right? So if we were to assume this and work backwards, we're going to run into a problem, because from here to here, we are multiplying by 1 over 12x. And if x is 0, that's undefined, and that doesn't make any sense to do, right? So since we don't have the proof of this converse written in front of us, we can adjust our statement. We could for sure prove that if x equals -4, then x is a solution to this, right? But typically there's no need to do that, because again, just proving the forward conditional statement will always give us a list of possible solutions, right? All we have to then do is go and check solutions, and usually there's not that many, so it's not that difficult to do. So typically all we want to make sure is we don't necessarily need everything to be an if and only if. If it's an if-then, that's okay. The forward direction still works. But if we are using an if-then that doesn't go both directions, then that's when we need to make sure we check our answers at the end, because that's when we could potentially have extraneous solutions like we do in the case of rational equations, radical equations, sometimes logarithmic equations, and different examples like that. And this is really the reason why it's these justifications that only go one direction and cannot simply be reversed on the paper. So hopefully you learned something. Hopefully you had fun taking a deductive perspective toward equation solving. If you have any comments or questions or suggestions, anything like that, leave them below. Make sure to like and subscribe, but most importantly, keep flexing those brain muscles, and I'll see y'all later.